Good morning, good day, good afternoon to everyone out there. It's a pleasure for me to have the opportunity to present to you within this webinar series the topic Substation Automation Solutions. From beginner to sales professional. Sales means not engineering, not troubleshooting, so I will you not bother with signal lists and communication telegrams and such things. Target audience are people new in this business or non-technical people who are curious about this topic and get a rough overview. I try to keep it very simple and will not to dig too deep into the technology or discuss special variants. Today we start the journey from the beginning, where the energy we will handle later with our substation automation solution, where it is born, where it flows, and where it finally ends. In my coffee machine at home, hopefully. So feel invited to join on the journey from the production in different types of power plants to our power outlets in our homes. Roughly the agenda, what you can expect, I have explained. So the first part you have successfully passed. In Chapter 2, I will explain the basic way of working of some electrical power production solutions, like conventional power plants, renewable power plants, and other plant types by using some nice photos and giving some explanation about the process. In Chapter 3 then, I will tell how the generated power will be transmitted over long distances, using devices to transform the generated power first into higher level to reduce needed current and resulting thermal losses, and afterwards step down again on a level we can use in our home. And finally, question and answers. Please write in the chat, otherwise we will get into trouble when we exceed the time by answering immediately and maybe starting discussions. And for sure, you can reach me via email, and any hints for improving this module or missing topics, please send also. Electrical power plants. These are the units where the electrical power is generated by converting raw materials into electricity. Unfortunately, except the solar panels on our balconies and or the roofs on our houses for private use, power plants are located somewhere where the conditions are good to produce energy, but these places are not always there where the energy is finally needed. As an example, wind farms can be offshore in the sea, or solar farms are installed in the sunny south. Types of power plants are, for example, conventional types using gas, coal, oil, nuclear power plants using uranium, renewables using wind and sunlight, biomass, geothermal, hydrogen and others. In the slide picture here you can see a photovoltaic power plant with connected high voltage transmission line in the back to transport the generated power. To understand this, and before we dig into the power plants and overhead lines and transformers' way of working, let us have a short look over the complete path from the power plant to the consumer. Here you see the path from the power plant to the consumer. Starting left, the energy we want to use in our households, typically of 100 volt AC or 230 volt AC, must be produced somewhere to be available in our power outlets. On the left-hand side, you can see the places of origin, the power plants. After being produced in the power plant, the energy needs to be transported. Transmission is a technical term for that, to the consumers on the right-hand side. To avoid loss of energy by having high current and resulting heat and thermal loss, the energy is transformed into higher voltage levels. Power equals voltage multiplied by current, as we learned in school, means in simple words, as higher the voltage, the less the current needs to be to have the power transmitted. Or vice versa, the lower the voltage, the higher the current needs to be. In Germany, for example, the transmission voltage levels are 110 kilovolt, 220 kilovolt and 380 kilovolt. But in some countries with longer distances, like China for example, voltages of 500 kilovolts and more are used. After being transmitted over the long distance, the voltage will be transformed down again into medium voltage level. In Germany, for example, 22 kilovolt or 11 kilovolt. The medium voltage transmission grid transmits the power to the needed places. In many countries, these medium voltage lines are cables in the underground. You are walking very often up top of them, luckily without feeling the power. Siemens substations for this medium voltage transmission grid are called primary substations. In some countries, the medium voltage level is designed with overhead lines, and there are outdoor substations using circuit breakers like STV7 or 3AF, reclosers like FuseSaver, and compact modular reclosers. And to make visible distances, the Siemens Bridges outdoor disconnectors. Maybe in a later module we will have a deeper look into this Siemens outdoor business with its power automation solutions like Fleiser and automated transfer switch. Let's see. And if you cannot wait, don't hesitate to contact the colleagues from the Outdoor Systems PLMOS in Berlin or watch the exhibition model in Schaltwerk Frankfurt. Substations in the connected medium voltage distribution grid are called Siemens secondary substations. There are three types: air isolated, gas isolated and blue GIS. So, after reaching the destination in the medium voltage distribution grid, the power will be transformed down again into the low voltage level we want to have in our house. This is a low voltage, number 3 in the slide, because no one wants to have 11 kilovolt or 20 kilovolt in their home. Low voltage in the houses is typically 380 volt AC, or the volt alternative current for ovens, for example, or the well-known 230 volt AC or 100 volt AC, depending on the country's implementation, for illumination or for the coffee machines, TV, PCs, radios and other electrical devices we are using daily. Now we had a short interview about the complete path. So let's start from the left to right and see some types of power plants. The first type of power plant I want to talk about is a coal-fired power plant. In these types of power plants, heat will be produced by burning coal. The coal is transported via ships or trains from the mining to the power plant. The coal will be pulverized to burn more efficient. The thermal energy generated by burning coal is used to heat water in a boiler and make steam out of it. This steam drives a turbine which forces a generator to rotate, and finally this rotating energy is converted using magnetic inductivity into electrical energy of a certain current and voltage depending on the used generator. The principle of a generator, let's say, this is the core element of the power plant, is to convert mechanical rotation via inductivity of magnetics into electrical power. Just a sidestep here, Siemens has nice generator circuit breakers with generator protection and control units. The colleagues in Berlin will be more than happy if you contact them to learn more. I will tell you some protection basics about this when we come to protection functions in a later module. So in a short summary form, the task of nearly any power plant is to get the turbines and the generators rotating by heat or also mechanical drive. After the power generation, a step-up transformer is connected, which transfers the power by using inductivity of two coils, primary and secondary side, into a higher voltage with less current level. The transformer ratio formula to calculate in the easiest way, power equals voltage primary side multiplied current primary side is equal voltage secondary side multiplied with current secondary side. And from the secondary side of the transformer, the energy will be fed into the transmission lines. Remember for later module, transformer protection and line protection functions. The next type I want to explain is a power plant type gas-fired. The energy production converting by heating water, rotating turbines and generators, and voltage step up by transformers is basically the same as for coal power plants. The difference is at the beginning of the process. To produce the steam for the turbine, gas is used instead of coal. Gas is transported via pipelines from the gas fields to the power plants, or be transported with huge ships as LNG, liquid natural gas. The gas will also not just burn in its original form. Remember, the coal was pulverized before burning, because efficiency will be very bad also. It will be mixed with air, compressed and burned in the combustion chamber under high pressure and high temperature. This hot gas will flow through a turbine and causes a generator to rotate. Calculating efficiency of power plants is a very interesting topic, and when you dig in, you will see that there are many variants and values. Oil power plants are basically comparable with gas, so I'll not explain in detail here to save a little bit of time. Coal, gas and oil-fired plants are called fossil power plants. The raw material is not anymore available after the electrical power generation process. As next we will see a hydro water power plant. Here in the difference, the used water is not converted and is still available after the procedure. Nice, right? In a hydropower plant, there is no heat used to rotate the turbines. Nothing is burned or prepared before, just using the mechanical energy by flowing water from top to down. It's environmentally friendly because no pollution will be blown into the air. And the used water is still available after the power generation procedure, which gives an unlimited sources of energy. The only topic to solve is to get the water efficiently back to the top reservoir. If there is a river to feed, everything is fine. If not, rain is needed, or also sometimes electrical pumps are used to pump water back on the top when too much energy is available and cannot be stored. The basic principle of a hydropower plant is that the water flows from a higher level to a lower level, and so converting the mechanical energy by rotating turbine blades, turning the mechanical link to a generator, which is converting its rotation into electrical energy, using the mentioned magnetic fields like before. This basic principle is known since hundreds of years, just in a smaller style, by water mills to grind grain into flour. The procedure from the rotating turbine onwards to drive a generator, using a step-up transformer afterwards, is comparable with the explained power plants types before. These types of power plants are used in countries with mountains and much rain, Norway, Austria as example. Now have a look into a nuclear power plant. Nuclear power plant uses heat produced by a chemical and physical process to boil water and drive turbines with steam. Because this procedure generates radioactivity, it must be handled very carefully to not release it into the air. When the atom is split, the resulting high energy is used to heat water in a water boiler. From here, the process rotating a turbine, generator, step-up transformer is comparable. So, maybe I repeat me, the basic way of a power plant is to get a turbine rotating somehow, and with that rotation, the electricity can be generated in a generator by using magnetic field. There are nice short movies in the internet or learning platforms about basic principles of generators and turbines. Now we come to another non-rotating way of producing electrical energy, the photovoltaic solar farms. PV photovoltaic is a version of power plants in this webinar which does not produce AC, alternating current, by rotating turbines, but produces DC, direct current, by converting sunlight in solar panels into DC by solar modules. But DC is worthless for coffee machines, ovens and so on. It must be converted from DC into AC with a DC-AC converter to be used direct in the household when the PV is installed on the house, roof or balcony. Or when it is intended to use at other places far away, it must step up using an AC transformer like we saw in the examples before. Just to be complete, there is one solar power plant type CSP, concentrated solar power, which is also working with heating water, producing steam and turbines and so on, like before. The procedure of a PV is a chemical process, converting sunlight into DC. The procedure of a CSP is physically based, converting the sunlight by using mirrors to heat water. But now, finally, for this module with power plant explanations, and we are running out of time, we will see some wind turbines and wind farm applications. For other power plants, when I've piqued your interest, like hydrogen, biomass and others, please have a look into the literature. A wind farm is acting again by using mechanical rotation to drive a turbine and a generator, like the hydropower plant. An advantage is that the rotating blades provide direct rotation, so we save the step to burn something or use flowing water to drive the turbine. Just catch the wind and connect mechanically. Smaller disadvantage is that we cannot control the availability of the resource wind. Same, by the way, like in the solar power plant. We need a solution to store the energy somehow in another type of raw material. Power to gas, just as a keyword, and make you curious. Yeah. Each wind turbine is in principle a complete power plant, because besides the wind blades, also the turbine and the generator are built inside the tower. installing many wind turbines nearby and connect the produced electrical energy together in a substation, it is called a wind farm. Wind turbines or wind farms can be on land, onshore installation, typically on higher levels of mountains where strong winds are available, or on the sea, offshore installation. An example of both types you can see in the slide here. The produced energy, alternating current luckily, from inside a wind turbine is transported via cables, underground or subsea, to a step-up transformer to be transformed into the transmission voltage level. In the next slide we will see an example of how to connect a wind farm to the electrical grid. This scheme is taken out from the very valuable document Siemens TIP, Planning of Electrical Power Distribution. The wind turbine number 1 produces the energy which is transported via cables to a medium voltage transformer number 2 to be stepped up to a connected medium voltage switchgear in number 3. You see many wind turbines coming there, where also the energy from other wind turbines is collected on a medium voltage busbar. In that switchgear many wind turbines are connected, and by using intelligent SCADA systems, number 4, it can be decided which feeders are connected or disconnected. By switching on and off the cables from different wind turbines, it can be controlled how many power will be forwarded to the transmission grid, number 7. In 5, there are meters to calculate the transported energy, to measure and for sure bill to the customers. Nothing is for free. What is missing here in this picture is the so-called BESS, Battery Energy Storage System. This we will see later. In the next slide, just as an appetizer, but also an essential part of our journey from generation to consuming, the application and location of a generator circuit breaker is shown. The power plant, as learned, is producing power, and because the voltage is low, the current is quite high at the location before it is stepped up into the transformer. And in case of a fault there are very, very high short circuits, and resulting the generator breakers are very big in dimension, up to 2.5 meter high and for 3 phases, and up to 4.5 meters wide, and having a total weight of around 7,000 kilograms. And the rated voltage in the medium voltage range, for example, is 3.6 kV or 17.5 kV. Siemens vacuum generator breakers are named HB3. Feel free to ask the Siemens contact for further information. Now we are coming to a topic which is new, because availability of renewable energy like wind and sun is not predictable as it is for other power plants. Battery Energy Storage System, BESS, means something like a rechargeable battery. Let us have a short look in such a solution. BESS are like rechargeable batteries, working like the accus in your mobile phone. They can store energy from different sources, hold it and discharge it when needed. For us, these modules can be part of automation solutions. So even when the modules are from SIEA, we are not from SIEA, we are able to integrate such modules into our substation automation and protection solutions. When sun and/or wind is available and the produced energy is higher in that moment as the demand, the energy can be routed into the BESS, instead into the transmission lines. A defined area including power generation, power storage, power transmission, transforming, distribution is a so-called microgrid. For that we have a solution called microgrid control based on the CCAM A8000 family. See you in a module later for this. At this stage, now enough talked about power generation and storage. Now let the electrons produced find their way to my coffee machine. Next slide will show the way of working of a transformer. A transformer is a static device that transforms electrical energy from one circuit to another. It works on the principle of electromagnetic induction or inductivity and can step up or down depending on the numbers of windings on primary and secondary side. As mentioned, power is generated at low voltage, medium voltage, 1 kV up to 52 kV, but on a high current level, and transmitting this directly will result in high terminal losses. The transformer steps this up, means using a higher voltage and lower current. Means lower heat and less terminal losses in the transmission lines. The optimum voltage level to use depends on the distance and the needed investment and overall cost calculation, return of invest. Transformers are quite costly. An example you can see in the slide. There are 3 different types of transformers mentioned. Typically they are installed outdoor, so maybe you can see one of them when you follow the transmission lines to their beginning or end. Good chance to find one at the borders of your city or village. Take your bike or go jogging along a line, and how such a line looks like we see in the next slide, and I'm pretty sure you also see them very often. Transmission lines are constructed on so-called pylons. Like everything in our engineering world, and not only herein, there is a standard for them. So also the pylons follow a European standard, for example here DIN EN 50341. There are the dimensions, materials, connections, and all this data described. Remember that we are dealing here, for example, with 220,000 volt AC, which is around 1,000 times higher than the 230 volt AC we have in our house power sockets. And when 230 volt AC can be deadly, it's not a good idea to come too nearby to 220,000 volt AC. So a pylon needs a certain height and must be very good isolated to not have voltage on the metal where humans or animals can touch. In Germany we have transmission lines on voltage levels 110 kV, 220 kV and 380 kV. Can you see which voltage is transmitted in the pictures? Count the numbers of isolators in series per phase. And there are always 3 phases belonging together. One isolator is 110, 2 isolator 220, and 3 is 380 kV. In the overhead line 110 kV example, on the slides the 3 phases are arranged vertically. Maybe phase A is on the top, B in the middle, C on the bottom, but this is just an assumption. The cables look the same. In the 380 kV example, you can see in total 4 systems, where I guess 2 are 380 kV and the 2 lower horizontal are maybe from a medium voltage transmission level, using the pylon together. Just to complete, when you find pylons with just 2 lines, or for redundancy purposes 4 lines, like on the right side, these are lines for train electrification. Then you will see maybe a train route nearby. In this area of application, the energy transmission system has not 3 phases, but 2. Now we come to the end of power transmission, and somewhere at the border of a city or village or huge industry area, the voltage is stepped down to medium voltage. From the step-down transformer, let's assume, for example, 220 kV to 20 kV, the distribution often is under the earth in cables. In some countries, medium voltage overhead lines are also available on pylons, or here the correct name is poles, because it is quite easier and cheaper and faster to mount. You see it on the left-hand side. But due to weather conditions, ice, heat, hurricanes, animals climbing on, and/or vegetation influences causes short circuits and resulting interruption of power flow, the trend goes also in direction to use underground cables. So we are concentrating now on this solution. For sure, when you walk through your city or village, you have seen such switchgears looking like garages, sometimes with nice graffitis sprayed on. Inside, there are feeders, transformers from medium to low voltage, measuring devices, and more. From here, we have the voltage of 400 volt AC for my oven, or the highly demanded 230 volt AC needed to cook my coffee. It just now must be routed in my house. Do you know where the fuses inside your flat or house are? Try to find out and check the data on the fuses. I guess something like 230 volt AC, and for short circuits, 16 amp fuse on the right side. I'm curious about your findings and maybe some photos in the chat. So finally, the journey ends and the power produced in a certain type of power plant reached our house. But on the way, many things can happen. On the way, so our customers, DSOs, TSO industry companies need a comprehensive power automation control, monitoring, and protection system. This is an outlook for future modules handling abnormal situations. And some of the abnormal situations are listed in the next slide. Just to make us curious for upcoming sessions, here's a list of potential abnormal situations, not complete for sure, and some protection functions to cover them. Thank you for listening, and I hope to see you again.